My name is Brett Kuntz. About a year ago, a little over a year ago now, I did a talk on convolutional neural networks and Swift and iOS 11 using this brand new API that was called CoreML. A lot has happened in the last year or so. So this is kind of intended as sort of an update to that talk. So if you're watching this on the internet, go find the other one first, and much of this will make much more sense. I'd like to thank you all for showing up today. I'd like to thank Lyft for hosting us and Kyle for pinging me randomly on the internet. Okay. So here we go. Yeah, like I said, I did this talk about a year ago. Basically, I'm going to just explain some of the stuff that I've been studying and whatnot, give you kind of like a training pattern for how, if you want to get into neural networks, how I think you should approach it. We'll do a quick review of neural networks in general and convolutions and how they're combined together to do image recognition. And then we're going to look very specifically at mobile image recognition, some different networks, stuff like that. And then at the end, hopefully leave you with some next steps and where to go from here. All right. Yeah, I did the talk on this for about 2 hours at AllConf this year. And so the theme was like you were entering a neural network Shaolin tempo. So that'll explain some of what these pictures mean. First, I think you need to know Python. I know this is a Swift meetup, but I think Python is the current language of data science. So if you're going to start anywhere, I think you need to know Python. I put roulette up here. I'd like you to know just some basic statistics, but if I tell you to study statistics, you'll end up like reading some math book and trying to understand different distributions, and I think that's kind of the wrong way to approach things. So like if you can go to a roulette table and put a chip down and you know what the odds are of winning, then I think you actually have a good real-world understanding of statistics. The same vein, I think you need to know the basics of calculus and linear algebra, but I don't think you need to like do a full-blown college course on this stuff. So just the 6 fundamental concepts of calculus, derivatives, limits, so on and so forth. Same thing for linear algebra. You don't need a full-blown college linear algebra course, but I think you need to be thoroughly familiar with how to multiply matrices and what's going on there whenever that happens. There's a course out there, Coursera, by Andrew Ng. It's kind of an academic course, but I think it's really probably the best place to get going. They have like 5 lessons or so. You pay $50 a month, you get in there. The second thing that I like about this course is that they have these sort of precompiled notebooks. So if you're not familiar with doing like Unix software and all this stuff, you can basically play in their sandbox a whole bunch for free until you get the hang of working with virtual machines and stuff like that. The Coursera course is based around Keras and TensorFlow, which is Google's matrix math library. What I've been doing a lot of last year is pytorch. So I had the honor, or managed to take the FastAI course earlier this year. And so I would say, like, if you want to take it up to the next step, just go through the entire FastAI course. It's free, it's online, it's on YouTube. The only price of entry you need is to get a virtual machine of some form. If you get a paper-space machine for 50 cents an hour, you can be learning, you know, and I would tell you to definitely put, you know, a few hundred hours into that. If you can go through those 2 courses, I think you'll have a very solid understanding of everything you need to know for neural networks, and you can basically go to anywhere you want from there. The next level above that is you're probably going to have to start reading papers or looking at a lot of other people's code. Practice. Kaggle is great for this. I would tell you not to do like the latest and greatest Kaggle competitions, but maybe do the ones from like a year ago, because then you can go out and look on the internet, see other people's code and how they've tackled these problems and stuff like that. And then finally, I think you just need to get out into the real world. Everybody in this room probably has some problem or problem domain that they know better than anybody else. You know, we're all mobile programmers, but everybody brings something different to the table. And so to me, what's cool about neural networks and stuff like this right now is that basically anybody can become a domain expert, in some oddball problem that only you understand. You don't need a PhD or any of this stuff that a lot of people say, this stuff is, even 5 years ago, dealing with all these libraries was a royal pain in the butt, but nowadays basically anybody can do it. There's different ways about thinking about all this stuff. This is roughly how I like to organize it. At your basic level, you have sort of, we'll say, just raw math, or your CPU, or maybe universal Turing machines or something to that effect. The next level up would be like a basic virtual machine, Coursera, Paperspace, running like a Jupyter notebook, where sort of the GPU magic is kind of abstracted away, but you're running on dedicated hardware. The next level up from that then, I think, is just cloud software, AWS, Google Cloud, dealing with multiple machines, multiple, devices to try and coordinate results. The next level up then, I think, is mobile development. I put it way up here above the cloud because a lot of times with the cloud, you can just cheat and throw more machines at a problem or something. Whereas if you're on a mobile device, you have very hard memory constraints, you have very hard speed constraints, and even if you can fit everything into those things, you still need to run everything at a very throttled manner because you can't want to use up all the CPU or all the power of the local device just to solve your particular problem. The next level up then, I think, is like custom hardware. This is where a lot of the people are super interested right now. So you have like Google with their TPU, NVIDIA with their Volta devices. There's a lot of machine learning hardware startups out there that have been in stealth mode for the last year or two. So I think we're going to start seeing a lot of custom hardware come to the market. So this sort of is the very, very bleeding edge. But, very broadly, I think we're up here on level 3. But the more time you spend on these lower levels, the easier it'll make for you to do stuff on a mobile device. Okay. Machine learning. Very broadly speaking, there are 3 categories of machine learning. What we're going to be talking about today is image recognition, which is a subset of supervised learning. Unsupervised learning is kind of not super popular right now, but it's mostly like clustering algorithms, stuff like that. Reinforcement learning is becoming very popular, but I'll talk a little bit about that at the end. Obligatory XKCD comic that's required for all things. I find this one more funnier the more machine learning you do. Anyway. So very broadly, we're going to take an input, numbers, picture, audio, video, some form, but a group of numbers. But we have known data. To use the canonical example, we have cat pictures or dog pictures, and we're going to combine this data together with a bit of math to produce some sort of magical black box. So we put in cat pictures, it says cat. We put in dog pictures, it says dog. In order to do this, we train the model. We show it lots and lots and lots and lots of pictures, give it feedback. That's what the training loop is. And then finally, at the end, we want to use it on an unknown dog picture, and it says dog. Our goals can be thought of as being quality, just how accurate our model is. But in particular on mobile devices, the size of our model, how many variables we're using to do our math, how many megabytes of data we have to ship down the pipe, and then the complexity, how many CPU cycles does our model take to run. Linear regression, you've probably seen this before, but basically fitting a line to a group of points. Linear regression comes up a lot because basically, if we can think of all of our cat pictures on being one side and our dog pictures on being on the other, and if we could somehow magically learn the slope of the line in between, that is what's called a perceptron, which was the original invention of neural networks back in the 1950s or so. This is actually not a field that's as new as we think. There's some interesting things you can do with single layer multi-node neural networks, but for most practical purposes, most real-world neural networks are 2 layers with two sets of nodes. So 2 layers with multiple nodes. The simplest example then is a feed-forward neural network. The data comes in, propagates all the way down to the end. There's no recursion. This is the tensorflow.js MNIST layers example. Last year I did a whole bunch of the MNIST with a basic neural network, so I'm not going to go deeper into this one right now. There's whole bunches of different neural networks out there. This is just a page showing some of the different variants. We're going to start at the far top left corner, go over and then sort of Z back to the very bottom with this deep convolutional neural network. So first we have our perceptron. Next we have our feed-forward neural network. This is just basically one input, one layer of nodes, one output. And if we look at our deep feed-forward network over here, this is the basis of most neural network architectures. We do a bunch of stuff to come up with some sort of input, 2 layers of feed-forward neural network nodes, and then a layer of output nodes. The second layer of this is a bunch of RNNs. You don't need to know that. Third layer is a bunch of variants of autoencoders. They've kind of fallen out of favor, but if you view them as like a precursor to GANs, then these are super interesting. This fourth layer has Markov models over there, which isn't really, I wouldn't lump that in with all these neural network variants. And then the rest of these you can probably ignore. But then we come down here to our bottom left corner, which is our full-blown deep convolutional feed-forward neural network. So basically we take an input, run it through some convolutions, use this layer of 2 layers of green nodes, same as our deep feed-forward network up here, and then finally we do our output. So this is some variants in neural networks, but this is the structure of most of these things. The convolution part is the second part of the trick. So last year I said that convolution was nothing more than matrix math. That's kind of a drastic simplification, I'll agree, but I think the basic concept that you need to get is that you can take one input and you get an input, you put an image in, you get a different image out. These are some different examples of smaller convolutions. The far one is a Gaussian. This one is like a Sobel edge detector. You don't need to know these, I'm just giving you some examples. This is one I think you can wrap your head around. We take the input image, which can be thought of as this far set of pixels. This convolution is just all ones. So that means that literally the output pixel, this 7 over here, is nothing more than all those numbers over there added up together. So we do that one, we get an output, move the convolution over one step, generate the next pixel, over another one, next pixel, so on and so forth. So this is, so 2 convolutions you need to know are this 3x3 striding, which sort of breaks up an image into slightly smaller chunks. This is an excellent GitHub repository which has a ton of information on this subject. Maxpool, this one's easy to pick up. We just take a cluster of, say, 16 pixels, pull the largest one out of each group to make a smaller one. So we take a larger data set and make it, squash it down. So if we take these 2 concepts, the striding and this 2x2 maxpool, we can combine them together to produce our first convolutional neural network. This one's called the vggnet, and it's a little bit, it's structurally fairly easy to understand. We take an input image, we apply two 3x3 strides, a maxpool, 2 more 3x3 strides, maxpool, 3 3x3 strides, maxpool, 3 3x3 strides, maxpool, 3 3x3 strides, maxpool. For our final fully collected layers, this node has 4,000 on each layer, 4,000 nodes. And then finally we have an output layer to link up to our results. This network is cutting edge in 2014. It's kind of viewed as being like a dinosaur by modern standards, I would say. because it's extremely data hungry, and it uses a lot of CPU. But conceptually, from taking a basic image, convoluting it down, adding the two neural networks, and then doing the output, I think this is probably the best way to understand the basics of a convolutional neural network. Last year, I talked about I did resnet for like 10 seconds, which wasn't really that fair to resnets. So I'm going to spend a little more time on it here. If we look at this chart, the far left graph is the VGG19, which is the cousin of the VGG16 that we were just looking at. It just adds a couple more 3x3 strides in the lower layers. The basic problem that the VGG network has is that each layer, the final result has to go through all the layers, if you will. So even if, say, the second layer up here gets the right answer, it still has to pass through each layer all the way down. So a little bit of error up here becomes a little bit of error here, a little more, so on and so forth, until it finally gets to the end. So because of this, the VGG is actually about as big of a real-world convolutional neural network as you'll actually ever see. It's just, they were pushing the limits of what was possible. So a team from Microsoft came up with residual networks, and the basic idea, if you look over here at this graph, is that we have these layers, they're now strongly connected. So this solid dark line can be thought of as all just being one large block. And then there's these three dotted parts down here. So what happens is that the neural network actually can learn, that's what the actual neural network learns whenever it does its training step. And so if, say, the first layer actually recognizes the object, basically the neural network can learn and just short circuit the whole network. What this means is that resnets are extremely, they can handle large amounts of noise. And so that's what makes them very powerful. The second trick that the resnets bring to the table is that they use this average pooling step at the end. So instead of doing the fully connected neural network layers, we do this average pool step. This is much cheaper in terms of CPU cycles, and it's much easier to evaluate. So as a result, these are literally an order of magnitude faster, order of magnitude easier to build. And the beauty of this ResNet approach is basically you can just keep on adding more and more layers until you get something that actually solves your problem. So this is a 34-layer ResNet, but you can basically take this network right here, stack it up 5 times to get a 150-layer network, and that's actually, like we'll see here in a bit, a fairly solid approach. I did a talk earlier this year on AlphaGo versus AlphaGo 0, and one of the big changes they made between the two versions of the engine was simply going from a CNN approach to a ResNet-style approach between AlphaGo and an AlphaGo 0. So conceptually, if we might imagine a single, say these pink blocks right here, as being like a single residual block within the AlphaGo thing, then it has, say, 40 of these blocks, and that was sufficient, plus a bunch of GPU time, to solve the game at Go. So ResNets, if you learn any one thing from this for image recognition, just say ResNets, and you'll probably, you have a good example. Apple has a nice demo of this in Turing Create. So if you're wanting to build one your own, you can basically download Turing Create. I'll talk more about Turing Create in a second, but that's another good way to get going. Okay, so hopefully by now I've kind of covered the basics of convolutional neural networks and how they're built. From here, we're going to go into mobile-specific networks. So basically, we're going to start adding more and more complexity with the goal of reducing the amount of CPU cycles that we're doing in our networks and increasing our accuracy. So everything from here is going to get more complicated for less, more and more marginal improvements. Last year, I demoed a basic neural network with MNIST, VGG, Inception Network, ResNet, and then mobilenets, as well as YOLO, but that's a object recognition network. I was excited about mobilenets, and I think my faith was, it's everywhere now, so I think that did that all right there. The three more general image recognition networks I would suggest you look at. The first is DenseNet. If you understand ResNet, ResNet actually uses an add operation in order to combine the layers. So we take that add operation and convert it to a multiply operation, you have DenseNet. This has some interesting properties for how error propagates through layers and reduces the error, but it also makes the whole network more computationally expensive. DarkNet is a image recognition network from the guy who created YOLO. What I like about this one is that if you look at the code implementation of it, it's about 17 lines of code or so. So you can literally just stare at it and hopefully obtain enlightenment or whatever. If you look at the fast AI sources, Jeremy has an implementation of it in there. UNet is another neural network architecture. It's probably better for doing like image segmentation, or if that's what you're wanting to do. But I think it's interesting because I think that's probably where things are going in the future, because it's a network that can be, you can throw more and more RAM at it basically, and it'll just expand to fill that up. So as pictures and images get bigger, I think this sort of approach is probably going to be where a lot of things are going to end up. So now we're going to look at a bunch of different mobile networks. squeezenet, it's one I should have talked about last year, but I didn't. We'll look at mobilenets again. And then 3 from last year, shufflenet, senet, mobilenets version 2, and then finally nasnet mobile. squeezenet is from 2016. It has this concept of these fire modules. Basically, they squeeze the entire network down literally, and then they expand to have these secondary layers. And then the whole network is a combination of about 8 of these sort of modules. Using this approach, they were able to reduce the amount of variables needed to make an image recognition network way down. So this one, there's a 5 megabyte version, which can achieve about 80% accuracy on ImageNet, which is pretty good. They even made another version of it where they sort of took that network and lobotomized it, we'll say, slightly, to get it down to half a megabyte, but still had decent accuracy. And it also runs pretty fast. This one is in TurinCreate. TurinCreate's a tool that Apple released in February of this year, I believe. They sort of took some of the good ideas out of Keras and scikit-learn with their core ML tools from last year and sort of made a unified tool. So if you're doing stuff for Swift and you only are targeting iOS, I would highly recommend you take a look at TurinCreate, because I think that's probably the best way to get going. I talked a bit about mobilenets last year. It makes heavy use of a concept called depthwise separable convolutions. Google released a new version of their TensorFlow library. I demoed this with TensorFlow proper last year, but now they have this TensorFlow Lite set of libraries, which are more targeted for mobile devices. So what's cool about TensorFlow Lite then is that there's an Android version as well. So if you need to be cross-platform, I think that's my current recommendation for what you should be studying. With iOS 12, Apple released CreateML. This is built on top of mobilenets. They have this sort of drag and drop GUI for like putting all your images into folders and dropping on there and hitting the run button. You should check that out. But if you're wanting to do something more complicated, I would advise you just to go to TurinCreate, I would say. This is shufflenet. This is a paper that came out late in the summer of last year. It's by a research group that's not particularly well known or famous, and so I don't think it got as much press as some of the other stuff, but they had some very interesting ideas in it. But basically they introduced this channel shuffle operator, which they then add to this sort of residual network style approach. And it makes heavy use of pointwise depth convolutions, which is a similar concept to the mobilenets, but slightly different, we'll say. And they were able to achieve a similar performance, well, actually slightly higher performance than mobilenets at about roughly similar cost in terms of CPU cycles and complexity. Here's a nice Medium article you can read if you want to learn more about that. senet. This is a paper to come out of the group that developed VGG, the Oxford Visual Geometry Group. They released it, the original version was last year, and it won the ICLR image recognition contest for that year. So they've finally gotten the accuracy of these networks to be up to around 97%, which is pretty impressive, considering where it was at just a few years ago. I would describe it as taking the concepts of squeezenet, but then using, say, something similar to densenet to combine the insides of the layers, and then adding the group convolution idea on top. They re-released a new version of this thing. I wouldn't recommend this for day-to-day use, but I think this is one of the ones that's, you should look into. The people who did mobilenets went for mobilenets, and they basically did a version upgrade to it. So it's slightly more efficient, slightly more better performance, and so on and so forth. Basically, it took the blocks and added, it went from like two-layer blocks to three-layer blocks with this expansion layer sort of trick here. My friend Mathis wrote a very nice write-up on the whole thing. So if you want to go into it, just go look at that. If you want to do, this is what we've been using for doing our projects. So I would advise you, if you're looking for what's cutting edge today, I think this is probably your best bet. And there's also TensorFlow Lite implementations, so you get both platforms as well. So yeah, all these people are doing all this stuff, trying to build all these different networks, and Google said, well, why don't we just put some machines in charge of doing this? And so this is nasnet, and NAS is Network Architecture Search. So basically, they wrote a computer program to literally go out and search through all these different types of architectures and just come up with the best possible combinations. So if you look at the actual nasnet architecture, I don't think you need to learn it, but it's like literally just this Frankenstein monster of 8 different concepts sort of just combined together by a machine in like a way that makes sense to a machine, but no PhD student would have ever figured that one out. But basically, by running this whole search algorithm, they were able to significantly advance the state of the art in the field. So we have this little black dot way over here. This is our original VGG network we were looking at. If you go up semi-diagonally, that's a resnet 152, which would be the larger version of that resnet 34 that we looked at. This black line would be roughly the state of the art for the last few years. And then this red line is basically what the computers were able to achieve, just given an ungodly amount of GPU time. Out of the nasnet research, Google did a couple of papers where they came up with different methods to do these architecture searches. They created a tool called AutoML, which they're pushing now, with the basic idea that you sort of upload your data, say, give me the best version, and you walk away and you come back and it's there. Then earlier this year, they took that same NAS approach and combined it with genetic algorithms to produce another group of architectures, of which one was called amoebanet. And so we were in this or sorry, I took the Fast AI course, and we entered this competition against, well, a bunch of different people, but yeah, Google came in first ahead of us with their mobilenet entry. So I think this is where the future of everything is going. It'll be more like humans trying to come up with clever new ideas for the machines to experiment with, but you know, I don't think you need to know this, but this is where things are at right now. Okay. So now we'll just go into where I think you should be looking next, you know, the future of all this stuff. PyTorch. I've done a lot of PyTorch this year. I like PyTorch a lot, but the process of getting a PyTorch, say, prototype to an actual thing that you can run on your mobile device is still pretty tricky, I would say. It's not terribly user-friendly. They've invented this tool called Onyx, O-N-N-X, as sort of this universal gateway in between all these different platforms. On October 2nd, they're going to have some sort of conference or whatever where they're supposedly going to release this. My guess is they're going to push Caffe, or rather Caffe 2, as being their universal solution. So you'll build your model in PyTorch, Caffe 2 will run it on the device for you, and then Onyx will be this middle layer that keeps everything happy. There's tools for various other platforms to convert their stuff to Onyx. The interesting player to me here is mxnet, which is the Amazon project, because I think they're kind of a dark horse out there, and they may yet like try to make a big play in this field. But you can take PyTorch, convert it to Onyx, and then convert it to core ML files. But I would not advise that for day-to-day use at this point in time right now. But hopefully soon this will change. The other big thing that's on the horizon is TensorFlow and Swift. For about the last year, well, about a year ago, eager execution came into TensorFlow. This is sort of, if you're familiar with the two platforms, they've sort of taken one of the key concepts of PyTorch and brought it to TensorFlow. And the last year has basically been them writing more and more things into this eager execution style model. They've officially put out the roadmap for TensorFlow 2, and it says this is where we're going, so that's coming. The thing that's interesting to me then is that Chris Lattner is working on a project at Google that's hopefully going to make heavy use of Swift's type safety plus LLVM to sort of bridge between these two worlds. TensorFlow as it currently exists is kind of like a lot of brittle C++ code, and generating optimized code for mobile devices is difficult. And so my hope is kind of the promise of OpenCL from a few years ago will come finally to allow you to generate stuff for your mobile devices. If you're interested more in this, there's a nice YouTube presentation on this at the TF Dev conference in May of this year. They sort of demo doing the TPUs and everything using Swift, so you can look at that. And then, yeah, I'm going to hopefully do a talk on this where we go absurdly deep here in a couple of months. If you've got convolutional neural networks down, then I think you should learn recurrent neural networks. GANs and reinforcement learning are super popular right now. I know lots of people are interested in them, but I think it's still kind of like a, you know, question mark, we'll say, to steal from the underwear gnomes. I think there's money to be made there, but I don't have a clue of how to do it. And then I think language models are really interesting. This computer vision stuff has like a ton of people that are really putting a ton of cycles into it, but you can generate language models fairly easily, and I think that's probably going to be the next big thing in a couple of years. And then, yeah, just off the beaten path. That's roughly what I've been doing. So that's basically all I've got for convolutional neural networks in Swift. So, yeah, you want to take some questions? Or, yeah.
Hey, I'm Steven. Thanks so much. That was good. I was reading about someone talking about iOS 12 and being able to use transfer learning for a model that was maybe built into the Photos app so that their model in their app was really small. Could you talk a little bit about what that means and what's new in iOS 12?
Sure. Transfer learning is where you take a network trained on one problem and then apply it to something else. So the classical example is you take a network that's trained on this vggnet data set, which is like 1.4 million things, and then you can easily retrain the model to solve problems usually. So it's trained on cats and dogs. You put it on your friends' faces, and technically under the hood it's sort of saying, this person looks 70% like a golden retriever plus 25% of a Labrador versus this other person who looks, that's kind of how it actually works, but it actually works really well in practice. So Tour Create does that, right? And then the next level up is Apple basically embedding some models on the devices, and then they can just ship down the differential difference in order to reduce the amount of data that's being transferred.
Anyone else have a question? Over there, on my way.
Oh.
So Latner's working a lot on TensorFlow at Google, and he said that Swift is going to be the first class language for TensorFlow. Now, if you wanted to get into TensorFlow, do you think you could just do Swift, or would you still want to beef up on Python?
Sure. TensorFlow itself is like a bunch of C++ libraries. And then Google's had to embed all these various C++ accelerated libraries. So they have like Boost and XLA and a bunch of random things like that in there. And so coding pure native TensorFlow is not super fun. So then Keras exists, which is just basically a Python high-level wrapper, I would say. A lot of people code in Keras because it's slick and it's easy. But ultimately, if you want to do anything that's outside of the Keras garden, we'll say, then all of a sudden you're into the weeds with the C++. So the Swift, I mean, their vision is, I believe, is to unify these two worlds. They want to use just one programming language across both things. I think the vision's good. It's going to take them a little while to get there. But yeah, I think it's definitely the future. As for where you would want to start today, I still think you should do all this other stuff. The concepts from all this Python stuff will definitely transfer over to the Swift world, far faster than all these tools will be rewritten into Swift in, then say, the next year or two.
One more? All right. Round of applause for Brett. That was awesome.
Yeah.